The Nebraska plains in 1884 were not just cold, they were merciless. Winter winds swept across the treeless prairie with nothing to slow them, turning the land into a frozen ocean where even the strongest cabins groaned under the pressure. Anders Bergstrom learned this truth the hard way when he watched his neighbor's brand-new homestead cabin, built exactly as the official manuals instructed, drop to 35 degrees inside, despite burning 8 full cords of firewood. And when summer finally arrived, the same cabin turned into a suffocating 90-degree oven. Everyone trusted the frontier wisdom of above-ground walls, a raised floor and a pitched roof. These designs worked in the forests of Ohio and Pennsylvania, where trees sheltered homes from wind and moderated seasonal extremes. But on the Great Plains, those same structures failed spectacularly. Across Nebraska, homesteaders repeated the same mistakes. They built by the book, then froze in winter, cooked in summer, and watched their fuel piles vanish. So when Anders, a quiet Swedish immigrant, announced he would bury half of his cabin's walls, people laughed. They called it the potato cellar house, a joke that spread across the settlement. But over the next 3 years, Anders would quietly combine Swedish earth-building traditions with indigenous designs, creating a homestead that stayed 65 degrees in winter using only 3 cords of wood, while remaining cool in summer with no fuel at all. This is how he did it, and what he understood about the earth that every other builder missed. The Platte River watershed stretched in all directions, an endless sea of buffalo grass and blue grama that had never known an axe. When the Union Pacific Railroad carried waves of homesteaders west in the 1870s and 1880s, they found a world unlike anything they had prepared for. There were no forests for building timbered homes. Any useful wood had to be hauled from the distant Missouri River bottoms or scavenged from thin cottonwood groves. Each trip costly enough to bankrupt a family before their first winter. The land itself defied Eastern construction logic. Beneath a thin layer of topsoil lay hardpan clay that cracked in the hot months and turned to sticky gumbo during rains. Prairie fires swept through every few seasons, clearing everything taller than waist-high grass. But government pamphlets and railroad brochures all pushed the same message: build a cabin just like you would back east. Settlers were told to erect standard frame houses using milled lumber from distant depots or to build log cabins if they could afford to freight timber across hundreds of miles of open grassland. Homestead manuals even included detailed, familiar drawings, gable roofs, raised floors, above-ground walls, tall chimneys, all structures that made sense in wooded states but were completely unsuited to the plains. John Harvey learned this the hard way. 3 miles east of the growing railroad town, Harvey followed the manual to the letter. He spent an entire summer hauling cottonwood logs from river bottoms and trading cash and labor for milled lumber. By autumn, he had raised a 2-story cabin with a steep pitched roof, sturdy stone foundation, and a brick chimney that had cost him $40, nearly 2 months' wages. It looked like a perfect frontier home. Until winter arrived. Prairie wind behaved differently than forest wind. Instead of slowing as it moved through trees, it accelerated across the flat expanse, striking Harvey's cabin like a constant icy river. His raised floor, designed to prevent rot, became a wind tunnel that froze the boards solid. The steep roof acted like a sail, catching every gust and vibrating through the structure. The tall chimney, which would have worked beautifully in calm woodland air, created a Venturi effect in the relentless prairie wind, sucking heated air straight out of the cabin and dragging freezing drafts inside. Harvey burned cottonwood, elm, and even scrub willow from the creek beds. He kept the fireplace lit from dawn until midnight, yet still woke each morning to ice in his water bucket. Condensation froze on the interior walls in delicate patterns, and food spoiled as constant freeze-thaw cycles ruined everything in his storage bins. When summer came, the misery simply reversed. The dark interior, built fully above the earth, absorbed sunlight all day. The raised floor cut off the home from the cooling mass of soil below. Heat pooled inside the cabin until the entire interior felt like a trapped furnace. Anders Bergstrom watched Harvey struggle closely. He had grown up in Sweden, in the hills of Dalarna province, where winters dropped far below Nebraska temperatures. Yet his grandfather's home, a simple turf-covered structure set partly into the hillside, had stayed warm with minimal fuel. Those Scandinavian houses used the earth as their ally, not their enemy. By excavating walls below the frost line and banking soil against the exterior, they created natural insulation and thermal mass that captured summer warmth and released it slowly over the winter. But when Anders first arrived in America, he too had been swept up in the belief that American methods must be better. Milled lumber seemed modern. Standard cabins looked proper. He assumed the traditions of his homeland were relics of the past. Harvey's failure shattered that illusion. By the second winter, Anders began to reconsider everything. All around him, settlers upgraded their chimneys, added more chinking, bought better stoves, and still froze. The issue wasn't craftsmanship. It was design. Eastern architecture simply didn't belong on Western plains. Everything changed when Anders discovered the abandoned earth-lodge depressions left behind by Pawnee bands forced south to Indian Territory. The sites were nothing more than circular dents in the soil, but Anders recognized their significance immediately. These had once been semi-subterranean homes, wood-frame structures buried partway into the ground, with thick earthen walls and grass roofs that stayed cool in summer and warm in winter. They were prairie-built and prairie-perfect. Anders realized that both his Swedish heritage and indigenous knowledge pointed to the same answer: build with the earth, not above it. The ridicule began the moment he started digging. Harvey and the other settlers gathered around his excavation pit, laughing that the Swede was planning to live like a badger. Anders said nothing. He simply kept digging, carving his foundation into the ground instead of on top of it. The ridicule began even before the first shovelful of dirt was moved. Anders Bergstrom's neighbors, including John Harvey, leaned on their fences, shaking heads, whispering that the Swede's project would sink him literally. They called it the potato cellar house, a mockery of a root cellar more than a home. They warned, with a mix of amusement and scorn, that come spring melting snow would flood the partially underground structure and turn Anders's winter haven into a swamp. Even the county land agent questioned whether such a dwelling met homestead requirements. The law was clear: a habitable residence was all that was needed. No rule mandated following a prescribed design. Yet skepticism hung in the air like the bitter winter wind. Undeterred, Anders pressed on. He dug 5 feet below the surface, laying fieldstone footings that descended beneath the frost line. This was only the beginning. The crucial problem loomed large: moisture. He had inherited the principles of Swedish turf houses: thermal mass, earth insulation, and minimal fuel, but the prairie was no Dalarna province. Nebraska's soils were treacherous: shallow topsoil over hardpan clay, prone to cracking in summer droughts and turning into an impenetrable, sticky mess after rains. And water, if mishandled, would destroy everything. Anders had to learn to let the earth work for him, not against him. The solution began with a principle he had observed in his homeland: drainage first. He remembered Swedish mill foundations, where gravel beds kept frost and water at bay. Following this memory, he hauled crushed limestone from a creek 12 miles away, breaking it into thumb-sized pieces. He laid an 8-inch thick bed of this gravel, extending 2 feet beyond the wall line in all directions. The gravel acted as a capillary break, preventing water from wicking upward into the foundation stones through the natural suction of the prairie clay. Above this, Anders set his fieldstone footings, each stone carefully fitted to its neighbor without mortar, a brittle material that would crack under freeze-thaw cycles. The walls rose in an innovative double-layer design. Inside, a conventional post and beam frame of cottonwood timbers, spaced 16 inches on center, supported the roof and interior structure. Outside, Anders replicated what he had seen in abandoned Pony earth lodges: sod prairie sod stacked like bricks. He cut buffalo grass and blue grama into blocks 18 inches long, 12 inches wide and 4 inches thick. The root systems, still alive, knitted the blocks together over time, turning them into a living, self-strengthening wall. Between the timber frame and the sod walls, Anders packed loose prairie soil mixed with chopped grass, forming a 24-inch thick thermal mass. Yet walls alone could not solve moisture problems. Anders studied prairie dog towns, marveling at how these small engineers kept burrows dry despite relentless rains. He adapted their method, digging a 1-foot wide 18-inch deep trench around his cabin, 3 feet from the wall. He filled it with crushed limestone, creating a French drain to intercept surface water. Around the perimeter, he graded the earth with a 4-foot apron of packed clay and limestone chips, sloping 6 inches over its length to direct water away from the foundation. This combination of French drain and graded apron would become the unsung hero of his design, keeping walls dry through storms that would swamp lesser cabins. Construction timing mattered almost as much as design. Anders waited for late October, when soil moisture was ideal, damp enough to pack firmly, yet not so wet that it would slump. He banked the earth in layers, compacting each lift before adding the next. By leaving the south face exposed, he captured winter sunlight while the north, east, and west walls received protective earthen coverage. This asymmetrical approach created a natural windbreak, deflecting the prairie gusts that had tormented Harvey's cabin the previous winter. When the first blizzard hit in January 1885, Anders finally tested his design. 6 days of sub-zero temperatures and horizontal snow hammered the plains. Harvey burned cord after cord of wood, yet his cabin barely reached 35 degrees inside. Frost-lined walls, food froze, and the family shivered in layered clothing. 3 miles away, Anders's cabin held a steady 65 degrees, maintained by 2 small fires that barely consumed half a cord of wood. The secret was thermal mass. The earth and sod absorbed heat during the day, released it slowly, and moderated the extreme swings of prairie weather. Anders's knowledge of physics, absorbing and releasing energy through dense materials, had turned observation and tradition into survival. The arrival of spring revealed additional advantages. While Harvey's cabin became a stifling oven once daytime temperatures rose above 70, Anders's home remained comfortably cool. Heat absorbed by the thick walls in summer never reached the interior, while acoustic insulation from the sod and packed earth silenced the relentless prairie wind. For Anders, energy efficiency wasn't a concept, it was lived reality. By autumn, the proof was undeniable. Anders's annual firewood consumption remained under 3 cords, a fraction of the 8 to 10 cords required by conventional cabins. The labor was significant up front: excavation, masonry, wall assembly, drainage. But these were one-time investments that paid dividends for years. Anders had solved the problem that defeated his neighbors, creating a home that harnessed the earth itself to fight the extremes of Nebraska weather. The roof, often overlooked, was another stroke of ingenuity. Standard homestead cabins featured steeply pitched roofs to shed snow, which rarely fell in these windswept plains. The large surface area captured summer heat, turning interiors into ovens. Anders opted for a low-pitch roof, a 6 and 12 slope, balancing drainage with minimal solar exposure. Cottonwood rafters spaced 18 inches on center-supported rough planking treated with pine tar. Above, he installed a suspended ceiling, split laths woven with prairie grass, forming a cavity filled with dried grass, cattail down, and soil. Over this, the turf roof went on, cut in 3-foot-long 18-inch-wide blocks, laid in overlapping courses, grass side up. Birch bark beneath served as a vapor barrier, shedding moisture while allowing the living turf to breathe. Inside, Anders applied lessons from indigenous earth lodges to the insulation. Vertical cottonwood laths, spaced 4 inches apart, held a mixture of dried grass, cattail down, and clay. This natural insulation regulated both temperature and humidity, creating an environment that felt alive yet controlled. A single window on the south face provided sunlight and ventilation, carefully positioned to maximize winter warmth and summer shade. By the end of the first full year, Anders's experiment had become legend. Neighbors no longer mocked the potato cellar house. They came to see it as proof that European knowledge, adapted with careful observation of indigenous methods and prairie realities, could triumph over conventional wisdom. Anders Bergstrom had created a home that was not only habitable but efficient, comfortable, and resilient. It was a testament to human ingenuity, marrying tradition with necessity, observation with innovation. And as the seasons passed, the cabin continued to function flawlessly. Winters were warm, summers were cool, and fuel requirements remained minimal. Anders's earth-sheltered design proved that survival on the Nebraska plains did not require blindly following a manual. It demanded understanding, adaptation, and the willingness to work with the land rather than against it. This was the legacy of Anders Bergstrom, a home born from observation, memory, and courage, rising from the prairie like a living sculpture. It demonstrated that ingenuity, combined with respect for natural systems, could create comfort in even the harshest environments. In Anders's cabin, the earth itself became the builder, the protector, and the quiet, ever-present source of life and warmth. The innovation of Anders Bergstrom's earth-sheltered cabin did not end with walls and roof. Every opening, every vent, every detail was deliberate. The window, the only source of direct sunlight, was framed with doubled timbers and sealed against the earthen walls using a mixture of pine tar and oakum. This created a moisture barrier, preventing rain or snowmelt from seeping into the interior. It was small, understated, and yet crucial, a single point where conventional design could have failed, but Anders anticipated the prairie's extremes. The summer of 1885 provided the first true test of the cabin's cooling performance. 12 consecutive days saw temperatures climb above 90 degrees, with oppressive humidity making outdoor work almost unbearable. Harvey's cabin, constructed by conventional methods, became a furnace. By noon, interior temperatures hit 88 degrees, leaving his family seeking relief in the shade, moving from porch to tree to field. Anders's cabin, in stark contrast, never exceeded 68 degrees, and by evening cooled naturally to 62, all without a single fan or mechanical system. The secret lay in the careful interaction of thermal mass, insulation, and controlled solar gain. The turf roof absorbed the sun's energy but transmitted little heat to the interior thanks to the insulation cavity beneath it. The thick earth mass walls, in constant contact with stable ground temperatures, acted as natural heat sinks, drawing excess warmth from the air inside. The suspended ceiling prevented hot air from accumulating at the roofline, while the birch bark vapor barrier stopped moisture from infiltrating the living space. Inside, the cabin remained quiet, calm, and breathable. Thick walls and a living turf roof muffled the constant, often violent prairie winds. Whereas thin-walled cabins rattled, moaned, and funneled heat inside during summer, Anders's home felt like a refuge, a sanctuary from the extremes of Nebraska. The natural materials, earth, sod, and untreated timber, actively moderated humidity, keeping the interior comfortable without the need for screens, shade structures, or water sprinkling systems that other homesteaders relied upon. Economic benefits became apparent quickly. While neighbors slowed or stopped work during the heat, Anders remained productive inside his comfortable cabin. Water consumption for cooling was minimal, and no additional investments in shade or auxiliary buildings were required. The upfront labor for excavation, drainage, and earth banking was substantial, yet one time. The cabin's efficiency returned that investment season after season, proving the superiority of design integrated with natural systems. Ventilation, another challenge in the harsh prairie climate, received equal attention. Anders created a dual-mode system inspired by the ingenuity of prairie dog burrows. Summer heat, winter winds, and the constant threat of prairie fires all demanded clever management of air. Low-level air inlets along the south-facing wall drew cool air from the earth-moderated zone, while ridge vents at the peak of the turf roof created a natural draft through the stack effect. The vents sat beneath the turf, above the birch bark vapor barrier, allowing air to circulate without compromising weather protection. During summer, this system maintained a constant cooling cycle. Air entered through the lower inlets, absorbed interior heat, and rose to exit through the ridge vents. The intake air, passing through earth-moderated zones, was 10 to 15 degrees cooler than surface air. In winter, the vents were sealed with wooden plugs backed with cattail down, transforming the cabin into a sealed thermal envelope. Every degree of heat generated by Anders's small fires was conserved, and the earth mass walls alone regulated interior temperature and humidity. Fire safety, another concern on the open plains, was ingeniously addressed. After witnessing a prairie fire devastate a neighboring homestead, Anders incorporated multiple layers of protection. The earth banks surrounding three sides of the cabin acted as a natural firebreak. The turf roof, kept alive and moist, resisted ignition from wind-blown embers. And the chimney system, cleverly positioned inside the earth bank, reduced the cabin's exposure to sparks. A horizontal flue ran through the north earth bank before turning vertical, capturing heat from exhaust gases and transferring it to the walls while maintaining minimal profile to the outside. Even tornado resistance was an unexpected advantage. Anders's low-profile, earth-banked cabin deflected the rotational winds that could lift and shred conventional structures. When a funnel cloud touched down 3 miles away in June of 1886, Harvey's tall, exposed cabin lost its roof and a gable wall, forcing him into temporary shelter for the following winter. Anders's home sustained no structural damage. The heavy sod roof, anchored by roots and weight, could not be peeled away like conventional shingles, while the rounded earth walls redirected wind over the structure, protecting occupants from debris and extreme noise. Anders also mastered seasonal solar control. The south-facing window, carefully positioned and shaded by the roof overhang, admitted winter sun to supplement heating fires while blocking high summer sun. The combination of controlled solar gain, thermal mass, and ventilation produced a remarkably consistent indoor climate. During winters, the sun's low trajectory and the stored warmth of the walls maintained comfort. During summers, the roof and ridge ventilation expelled heat, while the walls absorbed excess energy. Anders had essentially created a passive climate control system, a 19th-century answer to modern sustainable architecture. By autumn of 1886, the performance of the cabin had been proven through 2 full annual cycles and several extreme weather events. Fuel consumption remained minimal, 3 cords per year, compared to 9 cords for conventional structures. Maintenance was negligible. The living roof required occasional weeding, and drainage systems needed minor clearing only after unusually heavy rains. The earth bank walls remained intact, insulated, and resistant to frost heave. The cabin had survived blizzards, prairie fires, and a near tornado with no structural compromise. Anders Bergstrom's design was more than a home. It was a holistic system that integrated heating, cooling, fire safety, ventilation, and storm resistance into a single, coherent structure. Every element served multiple purposes. The walls stored heat, absorbed moisture, and deflected wind. The roof insulated, shielded from rain, and resisted fire. The ventilation system moved air naturally, and the site orientation optimized solar gain while minimizing exposure to harsh conditions. Through observation, adaptation, and ingenuity, Anders had demonstrated a fundamental principle, that working with natural systems rather than against them, produced superior results. While conventional homesteaders struggled, expending fuel, labor, and money to maintain poorly performing cabins, Anders achieved comfort, efficiency, and resilience. His earth-sheltered home was a quiet revolution, a blueprint for survival on the plains that harmonized human ingenuity with environmental forces. The cabin stood not only as a dwelling but as a testament to the possibilities of design informed by experience, memory, and ecological intelligence. Anders had transformed challenges, harsh winds, scorching summers, icy winters, fire, and tornadoes, into opportunities for innovation. His structure proved that even in one of the most unforgiving landscapes in America, a home could be both sustainable and livable, drawing strength from the earth itself. By the end of 1886, the potato cellar house had become a model for what was possible. Neighbors no longer mocked Anders. Some quietly observed, taking note of his methods, perhaps imagining how similar techniques could improve their own homes. His work bridged cultural knowledge, combining Scandinavian turf house principles with indigenous insights, adapted perfectly to the Nebraska plains. Anders had created more than shelter. He had created a system, a strategy for thriving in a seemingly impossible environment. The winter of 1887 to 1888 was unlike any the Nebraska plains had ever seen. From December 15th through February 20th, temperatures remained below zero for 67 consecutive days. On January 9th, the thermometer plunged to -32 degrees. Blizzards swept the open prairie every week, piling snow in drifts that buried fence lines and drove livestock into whatever meager shelter could be found. Wells froze solid, forcing settlers to lower heated stones on ropes to thaw water for survival. For Harvey and his conventional neighbors, the conditions were catastrophic. His two-story cabin, built with every timber and brick imported at great expense, became uninhabitable by New Year's Day. Despite burning 12 cords of precious cottonwood hauled 40 miles from the river bottoms, the interior walls were encased in ice, frost spread across furniture, and water buckets froze solid even beside the fireplace. The family had no choice but to retreat into the barn, huddling with cattle and horses for warmth. Across the township, 3 other homesteads suffered similar fates: claims abandoned, families relying on neighborly charity, or scrambling to survive the relentless cold. Anders Bergstrom's cabin, in contrast, offered sanctuary. Throughout the bitter weeks, interior temperatures remained between 60 and 65 degrees. Less than 4 cords of firewood sufficed to maintain this comfort. The earth mass walls, turf roof, and carefully designed ventilation system had been stress-tested through typical winters. But now, under extreme conditions, they proved their full value. The surrounding earth banks created a microclimate that moderated the brutal outside temperatures, while the living sod roof insulated against snow accumulation that would have collapsed ordinary structures. The economic implications were immediately apparent. Harvey's fuel costs soared to over $40, equivalent to nearly 6 months of a typical homesteader's income, while Anders spent just $12 to heat his home. Structural damage added to Harvey's expenses: $8 for chimney repairs, $15 for broken window panes, and $22 for frost-heaved foundations. Anders's maintenance costs were negligible, less than $2, mostly spent sealing minor gaps in the earth banks with pine tar. Meanwhile, the turf roof improved over winter as the root system strengthened, binding the sod into a more durable, resilient covering. The following summer brought a new challenge. Between June and August, temperatures exceeded 90 degrees for 43 days, with stifling humidity making midday labor unbearable. Harvey's rebuilt cabin turned into an oven, interior temperatures climbing to 95 degrees. His family retreated to a makeshift shelter in the creek bottom, trying to survive the oppressive heat. Anders's cabin, however, peaked at 70 degrees, allowing normal work and daily life to continue uninterrupted. The earth mass cooling system, which had kept summer heat manageable in ordinary years, now handled extreme conditions that overwhelmed every other building technology on the plains. Productivity, comfort, and safety remained constant. Word of Anders's achievement spread quietly but steadily. Neighbors began visiting his home during periods of extreme weather, experiencing firsthand the stability and comfort his design provided. Harvey himself arrived one January evening, his own cabin too cold for his children to sleep safely. He spent 3 hours inside Anders's living room, marveling at the stable temperature and absence of drafts. The once mocked potato cellar house had become a local legend. In March of 1888, County Homestead Inspector Robert Mills conducted a formal evaluation. His report compared Anders's cabin to conventional constructions, documenting fuel consumption, structural integrity, and habitability. The findings were clear: earth-sheltered construction outperformed standard methods by a remarkable margin. Mills recommended that homestead manuals be revised to include earth banking techniques as an approved construction method for prairie conditions. Adoption of Anders's principles began with families who carried cultural memories of earth-sheltered construction. A Swedish family named Lindström built a modified version 6 miles south, incorporating turf roof techniques from Dalarna province. A German family experimented with earth banking for their timber frame home, achieving significant fuel savings with less excavation than Anders's full design. By 1890, 7 homesteads within a 20-mile radius had adopted earth banking principles, each adaptation reflecting the builder's cultural heritage and available materials. Technical refinements improved upon Anders's original design. The Lindströms developed a standardized earth bank mixture, 60% clay, 30% sand, 10% organic matter, that minimized settling while maximizing thermal mass and drainage. Norwegian settlers created modular systems, allowing incremental improvements over time. These adaptations preserved the principles Anders demonstrated: thermal mass for heat storage and cooling, earth coverage for insulation and wind deflection, and careful water management to prevent frost damage. The legacy of Anders Bergström extended beyond individual homesteads. Agricultural extension services began including earth-sheltered construction techniques in their bulletins, newspapers published articles detailing the methods, and even railroad promotional materials acknowledged that prairie conditions required specialized building approaches. His work provided a clear lesson: designing with the environment rather than against it produced superior results at lower cost. Even as modern heating and cooling technologies arrived decades later, builders continued to incorporate earth banking and thermal mass principles for comfort and durability. Anders's approach, combining Swedish turf house traditions with indigenous knowledge and practical observation, became embedded in the region's construction culture. It demonstrated that careful adaptation of traditional knowledge to local conditions could outperform standardized solutions in ways that were economically, environmentally, and socially meaningful. By the end of the 1880s, Anders's home was more than a shelter. It was a testament to ingenuity, observation, and resilience. The cabin survived blizzards, summer heat waves, prairie fires, and tornadoes. It achieved comfort with minimal resources, cost, and maintenance. It transformed neighbors' perceptions, inspiring adoption and innovation that reshaped homestead building across the Nebraska plains. Anders Bergström's story is not simply one of architectural innovation. It is a story of listening to the land, understanding local conditions, and blending human experience with natural systems. His work reminds us that the most sustainable solutions often arise when we observe, learn, and adapt, rather than blindly applying standardized methods. The potato cellar house, once mocked, stands today as a symbol of wisdom that transcends time, a quiet revolution rooted in earth, grass, and ingenuity. As winter and summer continued their relentless cycles, the cabin endured, teaching future generations the enduring power of earth, observation, and thoughtful design. In Anders's legacy, the Nebraska plains were no longer simply a harsh landscape to survive. They were a laboratory for adaptation, innovation, and resilience. His cabin remains a lesson for all who seek harmony with the natural world: that human creativity, when applied with respect to the land, can turn even the most unforgiving environment into a place of shelter, comfort, and life.